My name is Bozidar, and this is joint work done with a bunch of my colleagues and our students, Anuj, Nikita, Leyang, Xenofon, and Francis. And actually, Anuj did all of the heavy lifting, and he couldn't be here, so I'll present for you. So we're going to talk about radio access networks and the power consumption. So the first thing I want to point out is the radio access networks are a large part of power consumption of cellular networks, which are all over. And so actually, it's very important to reduce their power consumption. The second thing I want to emphasize is that today, radio access networks are being virtualized and are running on commodity servers, so software and commodity servers. So, for example, AT&T has recently signed a contract with Ericsson, a multi-billion-dollar contract, to virtualize the servers. So all the AT&T servers in the US will be virtualized in a couple of years. So it is really a relevant problem today. And if you look in the radio access networks here on the right, they consist on virtualized one consists of two components. One is the amplifier, and so the radio part, which is analog amplifiers, converters, and so on. And they do consume most of the energy because they have to send at higher power. However, the server itself and the software still consume non-negligible 10 to 20% of the network. And so this is what we'll be focusing on today. Right, so we'll look at this part, and we'll see how to reduce the power consumption of the server itself. Now, as it's not the biggest power component, but still it's actually quite big. So some estimates say that there is about 2 million base stations, 5G base stations in China alone. So if you just reduce 1% of server power consumption in the energy consumption, you can save 44 gigawatt hours per year just in China alone, right? So even 1% of saving. So it is really an important topic. It's actually so important that it's on top of mind of all the operators and vendors in the world, and everyone is trying to reduce it. But what they do today, they really just switch off base stations where they're not used. So for example, at busy, like at nights or weekends or so on, they would switch off both the radio and the servers and so reduce the network coverage. However, there is another important opportunity, which is effectively to reduce the power consumption even in the peak times. So how can we do that? This is actually something that's confirmed by many vendors and operators. If you look at the network at peak times, most of the networks are heavily underutilized, even at the peak times, which sounds a bit counterintuitive, right? So we confirmed that with the measurements in Cambridge. So we effectively measured we used the LTE sniffer that was 2 years ago before 5G was deployed. We measured the amount of bits that were sent in every 50 millisecond interval. And we plotted the CDF here, right? So the maximum seen in a 50 millisecond interval, the peak was sort of 1 kilobit, right? But if you look at it, the median, so most of the 50 millisecond interval have less than 10% of the peak traffic. And many of those, so 30 to 40%, have less than 1%, right? So you obviously have to provision a network for the peak, but 40% of the time your network is sending less than 1% of the traffic. So it's a huge capacity for energy saving. But it hasn't been done, and this is because it's hard. So I want to explain you next why is it hard to do. So the first challenge is when you write the RAN radio access network software, it has very tough deadlines. So the deadlines are sort of tens of microseconds. So here we show a little bit why it's that. So if you see here on the left-hand side, we have a bunch of components, software elements that do sort of equalization, descrambling, decoding, and so on. And so they do a lot of work. And the unit of time in which 5G does this operation is called transmission time interval. This is 500 microseconds. So when the work is done, you see that there is a bit of slack at the end, and this is sort of order of tens of microseconds. So, and in the contemporary software systems, tens of microseconds, because these are not real time, is actually not that easy to achieve. The second challenge is that there could be spikes that come right from one interval to another. So if I switch on my phone, I create a lot of signal processing tasks for this server, and it happens all of a sudden, and if I'm not cautious, I can actually have too much workload. An important thing to mention is that if I miss this deadline, bad things can happen. So the phones can suffer, and moreover, because of a design-based station, the base stations could even crash, and we had a lot of these cases where they actually crash. Because they're optimized and assume these real-time situations. And the third thing, important thing, is that if you now start writing everything from scratch, maybe you can solve the problem. But these are, decades of experiences, and you're not going to have your Ericssons and Nokias rewrite the entire base station stack to address these things. So you really look for a solution that is more practical. And so as a consequence today, if you look at the sort of deployment manuals from all of these vendors, they just say do not do any power optimization on the server, run everything in the high power consumption all the time when you run them or switch them off. So there's a huge capacity to do something there, and that's what we'll talk about today. So how can we actually save energy? Now assume we want to do this. What are the energy saving knobs? So the first one is frequency tuning, also called P-state. So what we can do, we can reduce the frequency of a CPU core or multiple CPU cores and of what is called an uncore, which is everything else that is not a core, so like L3 cache and so on. And here on the table, you see that on the bottom line, we give frequencies of the uncore, and on the y-axis, we give frequencies of the core, and each of these squares gives you the watt consumed for different setups. So bottom right is the highest frequency, 150 watts. If you reduce it to a lowest 800 megahertz, you halve the CPU power consumption. So there's quite a scope for improvement there. The other thing you could do is use C states or sleep states. Now this is a bit tricky. They're light states, which is C1 and C1e, and on the figure at the top, on the top right, we show that actually they save very little. These are the middle bars in there. Whereas we are the red bar, we can save almost the half of the CPU power. So these states are not great. There's another sleep state, which is C6 states, which actually goes to a deep sleep. But the problem is getting in a deep sleep and out takes a lot of energy and time. And actually, it doesn't work well for the radio networks. And we'll leave the details in the paper if you're interested. So that's why we'll focus on the frequency tuning in this case. So the setup is then, once again, we have these networks which are actually, even at peak hours, not really busy. And we want to tune the frequency to reduce the energy. So how do we do it? We build a system called RENC, and the general idea is quite simple. We divide the time in intervals of 50 milliseconds, so several of those TTIs. And then we say in each interval, we either expect that the network is going to be in a high workload, which is actually not that high necessarily. Anything more than 1% of the observed peak traffic is high workload. We just don't do anything. We let it run at a high frequency, we optimize for throughput and so on. We don't touch anything. But if it's a low interval, and remember there's like 40% of these low intervals, where the throughput is less than 1% of the power, of the maximum traffic, we want to reduce the frequency to keep the slack at 10%. So what that means, again, the slack, so first of all, we ignore these pink intervals on the left, which are high load. We only focus on the low interval. And so remember, these blue blocks are our signal processing components. And then when we do signal processing, there is some slack time, which is a time remaining until the idle time, until the end of the processing interval. And so the slack is simply a relative, the idle time divided by the total time. And so we start by one frequency. Here on the left, we say CPU frequency being 2.5 gigahertz, and the slack time is 60%. So intuitively, if I halve my frequency, okay, I go to 1.2 gigahertz, my processing time is going to double. And so I'm going to reduce the slack, right? And so by reducing the frequency, I can reduce the slack. And I want to reduce it until it comes to 10%, which is the safe margin we established through experiments. So it's a kind of very simple principle, but there are several challenges. One challenge is how do you actually measure the slack? And we kind of have a couple of new techniques here. We actually measure the slack of interrupt-driven threads. So those are the threads which, when they're idle, they yield to a DOS. We built a novel eBPF-based slack measuring system where you have to actually measure the transitions from user to kernel mode and back using scheduled and switch hook calls. And it has to be done efficiently, otherwise the overhead of measuring is actually higher than what you save. So that's one contribution we did. And the second one is you have a lot of busy polling threads. For those of you doing user mode networking, there's a kind of the threads where you continuously loop. In these cases, typically, you will have functions at the beginning and the end that sort of call something at the start of a slot, end of a slot. And we do binary rewriting. And we basically see where these functions are called and actually get the information about the useful work at the beginning and the end of those intervals. So these are two techniques, details in the paper, that sort of help you measure the slack and make sure and actually have an accurate estimate. Okay, so once you estimate the slack, once you have a slack estimator, the question is, how do I adjust the frequency so that my slack is 10%, as we said. We want to get it to 10%. And so this is not trivial because you have different deployments, you have multiple sectors, you have multiple antennas, you have different bands. Even your software update may change how your software works, and you need to recalculate your frequency. So we have a very simple iterative algorithm. And so effectively, as we said, we only measure the slack in low throughput interval, the blue ones. And we measure over a period of time, minutes or hours even, and we just average the slack. And let's say at the beginning, the slack is 20%. And we say, okay, I'm going to reduce my frequency a little bit. And then I measure again. And the slack is 15%. And then I reduce again until I converge to 10%. And I do it only once, so it doesn't really matter how fast I converge, right? Very soon I'll get to the optimal thing. So it's a very simple algorithm, but sort of safe to get your thing. Then the other thing that we mentioned as a challenge is actually how do you deal with sudden spikes. So there are two types of spikes. One is the data plane spikes. They have a lot of traffic all of a sudden. And the other ones are control operation spikes. So I switch on my phone and there is signal search and all this. So for the traffic burst, so data plane spike, we effectively leverage the ability of the radio access network scheduler to limit to do the slicing capability, to limit the bandwidth it gives to the network. And the intuition is that basically the more packets you have to process, the more bandwidth and throughput you have, the more CPU consumption there is, and the other way around. So if we go to a low throughput, where we reduce the frequency, we also reduce, we throttle the network, right? Because we know there'll be very little traffic. If we make a mistake, we go to high throughput and we let everything go through. And the key thing here is to order these correctly. So before we go to a low throughput mode, we reduce the bandwidth, and then we go to low throughput mode, and vice versa. When we go back, we now first increase the frequency and so on. So there's a bit of careful engineering, but it's kind of doable. And we do similar things for the control operations. So so now you'll say, okay, well, you cheated. You said you're not going to touch the RAN, and all of a sudden you're looking into all these things around the RAN, and what, are you not changing the RAN? We actually did special care to leverage only open interfaces. So on the OS side, we use eBPF, we use binary writing, we use system calls, so there is no new functionality of the kernel. And similarly, on the radio access network, we use existing open interfaces. So as I said, throttling the bandwidth is actually a slicing capability that's already available through 3GPP or RAN interfaces. And similarly, we have other APIs in RAN that gives us information about these key events that are going to happen. So that's how we are able to react ahead of time. And then the other thing we need to know is really, when we measure the slack, we measure the slack of the key threads that are important for the performance. So we do need to know the names of these threads, and sort of and in case we do binary writing, the signature of these threads. But keep in mind, like if I want to go and talk to, say, Ericsson, right? They don't need to give me their code. They don't need to modify their code. They don't need to give me their IP. They just need to give me a signature of a couple of functions, and it's enough to deploy the system. So it's fairly non-intrusive, right? Okay, so now this is the sort of, you learn the sort of high-level intuition. You learn a couple of challenges, obviously many more details in the paper. So let me give you an idea how much we can save. So the setup is a typical setup that many operators we work with used. So they use off-the-shelf HP or Dell or others, telco-grade servers. They use Linux distributions with the real-time kernel patches and all that. We kind of used exactly the same software stack. We used Intel FlexRAN and Capgemini reference designs. Many of the different commercial products are built on top of those, so it's a pretty realistic representation of many of the solutions. In the lab, we deployed sort of 2 cells and with 11 UEs in total, and then we just measured evaluated the things. And another thing to keep in mind is that the CPU is not the only power consumption part in the system, so we also have memory and so on. And just for your reference, this is a rough power distribution in our service. Right? So the first thing, on average, across different scenarios, we see that we save sort of about a bit less than 50% of CPU power, and that's much more than C states or if you just run the server like that. But even if you look in the aggregate, right, we save 30% of the overall server power by running our scheme. And remember that 1 30% was 44 gigawatt hours per year. So it's actually 30% is quite a bit that you can actually save in these setups. Now you may ask, okay, what happens if you have, how does it depend on traffic? So again, obviously you have many results in the paper, but this is an example where we run 9 UEs connected and run continuous traffic, right? So that they stream videos. And even then you see that very often because of the buffering and network characteristics, we switch to a low power, right? And so on average, we save 32% of CPU energy, even at that time where 9 UEs actually stream at the same time, which is not, again, very, very common. And then also it's important to mention the performance is unaffected. So effectively, when we run RENC, you can see that the performance bandwidth and latency basically stays pretty much the same. So you don't have any visible affection because we act sort of just in time. So with that, I'll conclude. So effectively, the key takeaway point is that the cellular networks have low traffic in most locations most of the time, even in peak hours. And it's not really today, no system addresses this. So we are the first one to build a system that reduces the energy consumption and at fine granularity to address these use cases. And we can address up to 30%, we can reduce up to 30% of server energy consumption without really having any performance impact. And I want to leave you with with 2 pointers. So as a part of this research and the wider research, we built an instrumentation system for the RAN, which is also applied to a popular SIS RAN, open source, and we've pre-integrated there, and they're both open source. So if you're interested in this research, I invite you to kind of have a look and download and perhaps hopefully use some of this open source software. And with that, I'll conclude and thank you for your attention.